Okay. So there were some technical difficulties last time, but I went ahead and just clicked go live again, start streaming again. Yep, it's working now. Man, I think my whole so okay, so actually this whole time I was trying to live stream and it just wasn't working. Um yeah, wow. Here, let me play the audio so I can hear it. Okay, it's not peaking, so it sounds fine. Um yeah, okay. So on this stream we're going to be doing some I'm just checking my audio again, guys. I'm sorry. AVU control. Is it already open? Yeah, it is. Okay, bring it down to like 70. Okay, that seems. Yeah, seems pretty good. Oh. Okay. I couldn't hear myself for a second. CD, OBS. Sorry, I'm opening my management script because I have a way of doing timestamps. I can just press a button on my launch pad and do what's it called? And it'll do timestamps for me. Here, maybe I cat that file 2026. Add a timestamp. LS cat 2026. Okay, so it's not writing timestamps for me. Okay, I'm gonna have to troubleshoot that. I'll do it later. Whatever. Okay, so all right, we're doing Commodore 64 programming. We're learning Commodore 64 Basic. It's gonna be great. And yeah, so let me run this quick program real quick. This is what we've done. This is the fruit of our labor, right? We can display different colored bars on screen. Behold the program, Eke program. And okay. Live dashboard. Here we are. Mute that. Okay, anyways. Yeah, back at it. We're learning Commodore 64 Basic. Do some writing. I want to clear and go home. And man, it just looks bad. Gosh. Okay, so last stream in quotes, right? I told you I did about 30 minutes of live streaming before this, but it just never picked up the fact that I was streaming. Maybe we want more contrast. More contrast, more gamma, less contrast, more contrast. Yeah, it definitely makes it look more vibrant with more contrast. More sat, less sat. Ooh, less sat looks better actually. Less gamma. Just shave it down till the black visible again. Like the contrast knob is actually the most important one. And the screen looks like purple also, so maybe we hue shift it. Reset the hue shift. It is also just still a bit bright, so maybe even Bump the gamma down. Reset the hue shift. Yeah. What am I? OBS streamer? Like I just stream about OBS. That's horrible. Gamma up. Sat. Normal saturation. It definitely does need some more saturation. And contrast. It's gamma, less contrast. A little bit more gamma. Okay. The text looks nice and legible again. At least it looks more legible. I don't know why I'm typing LS. Here, it's clear screen. Okay. Now, peeks and pokes. No, we're not talking about jabbing the computer, but we will be able to look around inside the machine and stick things in there, just as variables could be thought of as representation of boxes within the machine where you placed information. You can also think of some specially defined boxes within the computer that represent specific memory locations. The Commodore 64 looks at these memory locations to see what the screen's background and border color should be, what characters are displayed on the screen, and where, and a host of other tasks. By placing, poking a different value into the proper memory location, we can change colors, define and move objects, and even create music. These memory locations could be represented like this, and it gives us a nice little grid of boxes. On page 60, we just showed 4 locations, two of which control the screen and background colors. Try typing this, okay? We'll type that. Poke 5 5 3 2 8 1 7. Boom! It turned it yellow, and that looks heinous. So let's 5 3 2 8 1. And let's make it like a nice red color. That it still looks pretty bad, but it's not as like caustic to the eyes as the yellow was for you guys. I'm sorry. Okay, sorry, I'm tweaking the color again. Okay, 0 hue shift again. Ugh, I don't know why I keep messing with that. There we go. Okay, yeah. Let's poke it back to dark blue. 3 2 8 1 with what's dark blue? What's the color code? Is it 6? Okay, so it's standard. Looks fine. Alrighty. And is there a way I can get rid of those little like lines on the edge? Lowering the contrast, raising the contrast, lower contrast, raise gamma, raise sat, run, printing colors, and they look pretty washed out. Maybe if I bump the brightness just a hair. Might that be the best we've ever done? You know, it looks like washed out, but the colors are legible. You can like read them. Here, if I want to start typing in a different color, you can read it pretty much off rip. You know, I think we might have landed on something here. Wait a second. Color correction. Maybe just add some gamma. Nope, no need to add more gamma. Lower the contrast just a bit. No, we'll keep it like that. Increase brightness, increase saturation. No. Saturation, we do want the brightness tweaked up a bit. Saturation, also a bit. And okay, yeah, the black is hard to read. So if I type hello, right, it's a bit difficult to read, but if it gives you any solace, it's also a bit difficult to read on my CRT. So, you know, we take what we can get. And sort of, yeah, the brightness, Contrast up, contrast down, gamma up, saturation down, saturation up. And I just want visual clarity. I decided visual clarity is what matters most. We don't need to care about all the specific colors. Okay, let's just try. Okay, so this is the standard color. Add it here. Let's add another color correction on top of it. Color correction 2. And that will increase the contrast. Decrease it. Reset it to default. Increase the brightness. Defaults, increase saturation. Definitely not that. Defaults. U-shift. Definitely not that either. Defaults. Whatever. Okay, well, it's readable enough. So let's make this new program. We'll say new, and I will clear our screen, and then I'll start typing. So I'll say 10 for BA equals 0 to 15. 20 for BO, 2 spaces for some reason. No, just 1 space. I don't know why it added 2 spaces in the manual there. Equals 0 to 15. 30 poke 53280 with BA. 40 poke 53281 with BO. 50 for X equals 1 to 2000. Oops. Next, X 60. Next, B0 colon next BA. Okay, so this is just going to go through various colors. So to tell you a bit about this program, so I'll try to explain. So line 10, we wrote out, we're doing a for loop. We initialize 0, BA to 0, and we go to 15, and it increments by 1 each loop. Then we have a nested loop, which increments B0 by, which starts with B0 at 0 and brings to 15. Okay. Then we poke 53280, which changes the border color, and then 53281, which changes the background color, with the values 0 to 15, right? So it'll show us every single combination of 0 and 15. That's what these 2 pokes do. And on line 50, we have for X equals 1 to 2000. And this is just going to add some delay into the program. So then I can just say run. And you'll see it just goes through. Oh, next without 4, error in 60. Here, wait, did I mess? I think I might have messed up a line. For BA, maybe I said B0. BO. Next. BA. Run. Okay, so now it's just sort of cycling through the different background colors. Oh, that looks bad. That looks bad. That also looks real bad. That's the standard. That's readable. Bad, but not readable, but not good. Pretty readable, actually. Horrible. Fine, fine. Bad, real bad. Not as bad as you'd think. Okay, it's same color on same color. And does that, okay. So now we're changing the border color and cycling through. And in fact, here, I'd like to stop the program, list the program, and then I know you guys can't read this well, but just bear with me. I'm going to increase the speed by 10x. And it's just going to flash through them real fast. Just so we can get through them. There we go. So we're changing the background color. Changing the border color as we're going. And, you know, just because I'm concerned about the flashing colors, we'll go ahead and stop it. And then it's funny, this is actually a very readable display. It looks wonky, but it does the job. Now we can peak values as well. So we can say peak 53280 print peak, or yeah, wait, here we can peak 53280 244. All right. We also, this is displayed in binary and it looks like it's not what we want. So we'll say question mark peak 53280, and we want to and it with 15. Oh, we can't do and like that. Peak 53280 and with 15. So yeah, so right now we're on color 4 for the background. And here, let's list our program again. And let's like 5x the speed. So let's make it, or 3x this, or slow it down by 3 times. Let's change it to 6. There we go. Clear it. Okay. So, let's start program. Okay, so basic. Okay, so the language basic on the Commodore 64. You know, I want to do something like print 2026 minus 1982 is 44. Okay, so now I have that. Okay, Commodore 64 Basic. It was a, all right, no. The programming language Commodore Basic. No. Okay, the basic programming language is actually really quite powerful. So even though it was released 44 years ago, it's actually more powerful on the machine it's working with than many of our modern languages today. And that's because of these 2 instructions right here, peek and poke. So look at this program. I have this program written here. So it has lines 10, 20, 30, 40, 50, and 60. That's what these first numbers are. The instructions we care about are here. These are 2 standard for loops, but here's the instructions we care about. So on basic, you can peek and poke these different values. Now, what are these values, you might be asking yourself? These are literally memory locations. So on a modern computer, you have like virtual memory when you're running a program. You have all these kinds of safety features where, you know, you can't like execute any portion of memory. You have all of these different ways to make sure the program is behaving itself and not doing things it's not supposed to. But no, on basic, you're very powerful. You can do whatever you want. You can poke values directly into memory. So with this program right here, we're poking values, the value of BA and B0 here, directly into 53280 and 53281, the 2 memory locations, using our poke command. Well, with this program, if we run it, you can see it'll go through and change the background color in Commodore 64 Basic. And this is like working on the level of the OS, the level of the hardware is being changed based on this little programming, based on this little program we've written. And this isn't really something you can do in modern languages very easily. Like, show me how you can write to a memory address in Python. You can't, but you can do it in Basic. All right, I'll low-key make a note of that moment. I might want to clip. I might want to clip part of that. I'm trying to like make some more clips. There's a number of things I need to do, you know, in order to make the stream more accessible, more viewable. But yeah, so this is a fine enough background as it is now. And actually, man, we have this like we have this now. I think because the gamma's too high. So I've brought the gamma down a little, and I might even run it again. So it looks actually quite a lot better. The pink and the green are just never going to look good, nor the red. All of the like pure bright colors are just never going to look good coming through. But I think we have hope with some of these colors. Yellow looks surprisingly good. Dark red. All right, let's stop it there. We have this dark gray, and it looks pretty good. So, anyways, let's keep writing this program. So how about this? 25 print chr. Oh shoot, no, print chr $147. Man, I'm just a glutton for fussing with settings, aren't I? It's just a little fuzzy, so maybe adjusting the contrast, no. Saturation, no. Gamma up, gamma down, contrast up, contrast down. Saturation down, saturation up. No. Brightness down, oh, no. Definitely changes something about it. Okay, whatever. CHR 147. I think after the stream I'll look for like a filter. Because surely someone has tried to stream Commodore 64 before and come up with something. So border, bam, and then peak 5 3 2 8 0 and 15 background equals space peak 5 3 2 8 1 and 15, and then run. So now it'll print as well. Nope. Stop it there. List our program. Huh, why didn't it do that? List again. Run. Syntax error in 25. Okay, let's see what we wrote in 25. Print chr $147 border equals space peak 53280 and 15 comma background space peak 53281 close parentheses, enter. List 25 print chr dollars shift $147. We're just going to rewrite the line, not a big deal. Semicolon space border, oops, it's that key, equals that, semicolon peak 53280 and 15. Background equals quote semicolon peak 53281. Oh, we need friends 53281 and 15. Right, let's go back down. Let's start program again, and it cuts off. So I'm thinking, man, how do I get a couple more characters? Here's an idea. We'll change this statement to a question mark. 53281. And clear. Okay, that should be pretty good. So now it's going through and telling us that, but it's our background color is not printing properly. Because we're not able to AND it with 15. So I might actually split it into 2 separate lines, but honestly, I don't care that much. All right, so let's stop it at when it gets to like a nice combination. That's good enough. Okay, screen graphics. In all the printing of information that you've seen so far, the computer normally handled information in a sequential fashion. One character is printed after the next, starting from the current cursor position, except where you asked for a new line, or use the comma in print formatting. To print data in a particular spot, you can start from a known place on the screen and print the proper number of cursor controls to format the display. But this takes program steps and is time-consuming. Just as there are certain spots in the Commodore 64's memory to control color, there are also locations you can use directly to control each location on the screen. Since the computer screen is capable of holding 1,000 characters, 40 columns by 25 lines, there are 1,000 memory locations set aside to handle what is placed on the screen. The layout of the screen could be thought of as a grid, with each square representing a memory location. And since each location in memory can contain a number from 0 to 255, there are 256 possible values for each memory location. These values represent the different characters the Commodore 64 can see. By poking the value for a character in the appropriate screen memory location, that character will be displayed in the proper position. Okay, so we have this nice graphic where each line, so it starts off at 1024 and goes to 2023 or 2023. So we have a nice little formula where we can do column and row, where X is the column and Y is the row. Therefore, the memory location of the ball is 10 plus 20 plus 480 or 1524. So we can poke the screen just by doing that. Okay, so we'll poke the memory location 1524 with 81. Ooh, we put a ball there. And then we can poke 55, 7, 9, 6 with 1. And that changes the color of the ball to our background color. Oh, okay. Filters, new color correction, yes. Need some more contrast. More contrast and less gamma. More contrast, less gamma. And I'm doing this in like a separate layer. You can see it a bit better now. Quite frankly, you can see the whole screen a bit better now. Maybe this is actually the key. Here, let's just do a quick like color cycle. Black. Oh, that looks good. That looks good. Looks way better. Oh my gosh, that looks awful, but it looks bad on the Commodore 64 screen too. So looks great. Looks amazing. Looks surprisingly good. Oh gosh, I think I might have cracked it. Might have cracked the code here. Okay, we're doing background colors now, but that's fine. Light green. There we go. Okay. You know what? We'll clear the screen again. And why don't we go to, what do we want? There we go. List. So this is our program. I guess we're not dealing with the program. So, all right, so we also have the color memory map. You have placed a character directly into screen memory without using the print statement. The ball that appeared was white. However, there is a way to change the color of an object on screen by altering another range of memory. Type this to change the ball's color to red. So here, let's poke our ball back onto the screen. Poke 152481. So we have the ball on the screen, and then we can change. Right now it's a yellow ball, so we'll poke it to 55 796. Yeah, so now it's a white ball, or it should be white, but you know, it's our. We've got a bit of a. It's a bit of a situation here with our colors. The easiest would be just like a color map, wouldn't it? Or I could like, you know, have a nice clean signal and then just map various colors to various things. Whatever. Okay, as is fine. I can fuss with this later. I'm not gonna spend the whole stream fussing with the fucking colors. Poke 55, or I'm sorry for cussing. I should make it a family friendly stream, shouldn't I? Okay, the ball's red now. Poke 55 796. Oh, it's teal now, or it's cyan now. So for every spot on the Commodore 64's screen, there are two memory locations, one for the character code and the other for the color code. The color memory map begins at location 55296 and continues on for 1000 locations. So here's another grid of the color codes. And they use the same color that we used to change the border color to. So, all right. So here's a program that runs with screen pokes. All right, so let's clear our screen. New. All right. So we'll do 10 print, and then we're in quote mode. We'll print clear home. 20 poke 53280 with the value 7. Poke 53281 with 13. So I'm guessing that changes the background color and screen color. Okay, and it's saying it changes it to light green with a yellow border. So that's something we absolutely don't want. Here, how about we change it to, we'll change that to 0. We'll make it black. And honestly, let's just run and see what it looks like. Oh gosh, yeah, here, let me fix this. Black border, black field. Okay. This should be white on black, but it's currently light gray on black, and it looks pretty pleasant to the eye actually. So I don't think I mind it. Anyway, so we'll start off by poking that. In 30, we'll say x equals 1. And we're defining some variables here. Y equals 1. 40 dx equals 1. dy equals 1. 50 poke 1024. What is it? Plus x plus 40 times y with the value 81 and 60. Poke 10. Oh, and then for t, and I'm guessing this is just a little, what's it called? Little delay here. T equals 1 to 10. Yeah, it is. Next. Line 70. We're going to poke 1024 plus x plus 40 times y with 32. And I'm guessing this is, we've written a ball, we've waited a second, and then we've overwritten the ball. We've made it a space. And on line 80, we'll update our x to be x plus dx. On line 90, we'll say if x is less than or equal to 0, or x is greater than, or goodness, equal to 39, then dx equals negative dx. Okay, so here's what this line is saying. It's saying if x is outside of our like range, so here. So here's the program so far. So we cleared the screen, and then we set the background color, and then we initialize x and y to the top left location of the screen. So it's going to be like right here. Our ball will start up right here. Then we initialize dx and dy to, add 1 to both directions. So it's going to move it. It's going to draw it. So yeah, we initialize our dx dy. We draw the ball, wait a second, and we overwrite the ball. Then we move the x by that certain amount. And then we check to make sure it's not it's not going to be out of bounds, right? So we'll also do the same for y, where we'll move y equals y less dy. 110 if y is less than or equal to 0, or y is greater than or equal to 24, then dy, man, I keep hitting the wrong layer key to get to my equal sign. It's mapped to like, what is that? 12, 11, 10. It's mapped to F9, or sorry, to F10 for some reason. And then go to 50. Okay, so let's explain this program that we've written here. So this is what's really powerful about Commodore Basic, is that you can write directly to screen memory. So let's see that in action. So we start off by printing this key, this inverted heart, which is going to actually clear the screen. So it's going to make the screen completely blank. Then we can poke directly into the memory addresses. So this statement here, poke 53280, 0 is saying in memory address 53280, write the address 0. So, you can't do this in modern programming languages. You can't do this in Python, can't do this in JavaScript. You might be able to do it in like C++ maybe, with some extensions, but modern operating systems like Windows, Linux, Mac OS, they all use what's called like virtual memory or something like that, where you can't actually access direct memory addresses. But on like Commodore 64, on BASIC, you can. It's a much more powerful language. So it's super cool. So we can write directly to the memory location like this. So we write to these two memory addresses, which what these two do is it changes the background color. Then we initialize some variables. X is 1, y is 1, dx is 1, dy is 1. And then we do some more poking. So what this does, 1024 plus x plus 40 times y, we write the value 81. So this writes a ball to the screen. And we have a whole slate of memory addresses, right? The screen of the Commodore 64, it's a grid. And we have all these memory addresses where we can write to them. and it just updates the screen automatically. We don't have to print stuff out. We can just update the memory address. Again, another thing you can't really do on a terminal. It's a completely different way of thinking about computation and how doing graphics. Then for t equals 1 to 10, next, so we'll add some delay. Then we will clear the ball, right? We'll get rid of it. So on the next frame, we can draw it in a new location. That's what this line does. Update x by adding dx. Check the bounds because we don't want our ball to just go in one direction infinitely. Draw y. Again, we don't want it to go in one direction infinitely. And then update y and then check it. We don't want it to go in the same direction infinitely. And then line 120, go to 50. So, all right, so you're looking at a basic program like this, right? And you see all these numbers at the beginning of these. What are these? So this is your line numbers, except in basic, you write the line numbers manually. You don't have an editor manage the line numbers for you. So that makes it really powerful, where we can just say, go to line 50. And there is go to in other languages, but it's fallen out of favor. And here, if we run this program, we can see a lovely little bouncing ball just going through the various corners of the screen. And before you ask, yes, it's also flashing on my CRT. Basic is a slow language. One thing that you're missing, though, is that the CRT, it has a lovely little ghosting effect. So you can kind of see if you squint, there's not, if you even squint, like if you look pretty hard, there's a little trail that like follows the ball as it moves throughout the screen, which I think is a really lovely effect. But yeah, so now we have this ball going around on the screen. Pretty cool stuff. And in fact, here, let me think of how we want to do that. You know what? No, I'm not gonna go too far in a direction like this. So, all right, yeah. So this in the book, it just explains the code, and then if you change dx or dy, the ball will bounce straight instead of diagonally. So yeah, we can try that. So dx here, why don't we make it move up and down vertically? 0. So we just rewrote the program just like that. And now it's going to go up and down vertically. List, and then make it equal to 0. Make it equal to 1. Oh. Here we go. Run. So now it's going to bounce horizontally. Oops. I don't want that. Escape. Stop our program. Let's do it again, and we can even make it bounce faster. So here, let's say we want it to move like very quickly in the y direction, but comparatively slower in the x direction. So you can change dy to 2. So now you can see it's really moving. Bam. And interestingly, here, why don't we stop it? Why don't we make the border color into 1? Oh, run. Okay, list. What did I do with 20? Oh, I somehow got rid of the poke. Okay, well, let's... We want POKE, poke, and let's make that into 1. Make sure the program list's fine. All right. Okay, so now we can see our screen borders more clearly. Perfect. Lovely. Okay, so we can also add a little more intelligence. So far, the only thing you checked for is the x and y values getting out of bounds for the screen, and for the following, for the x and y bounds getting for the screen. Okay, it seems to have corrupted this line again. I don't know why. Anyways, 1, 2, 3, 4, poke. All right, so now we can add some lines. So 21, right? So I told you have to manually write basic lines. Here, let me write something down IRL real quick. Okay, yeah, line 21 for L equals 1 to 10. Line 25, poke 10, 24, plus int R&D 1 times 1000. So we want a number between 0 and 999. And 66 screen code. I don't know what that means. 27 next to L. 85 if eq 1024 plus x plus 40 times y is equal to 166, then we're going to the end of the line and start appending to it. Then dx equals negative dx colon go to 80. Okay, so line 85, it wrote correctly. And line 20 didn't corrupt either. Okay, perfect. And then line 105, if peak 1024, 1024 plus x plus 40 times y equals 166, then dy should be, oops, equal to negative dy and go to 100. So what we've done is we've added some blocks onto the screen. And oh, we still have dy equals syntax error. Oh, it's because it's the blocks are on screen. Here. Now we'll list. Okay, so there we go. Let's change dy to 1. Go to the bottom, run, list. Okay, I don't want to rewrite poke, so I'll just write question mark. So yeah, now we have our ball. It's bouncing around, and we added a bunch of random placed blocks. And you see right there, it just bounced off one of the blocks. Just bounced off another one. Bam, beautiful. So actually with this, I think we have everything we need, you know, to write like Brick Breaker, you know? That would be pretty cool, I guess. I'd like to make it not so flashy. Oh, sprite graphics. Okay, so, all right, we have 30 minutes left. I think instead of doing sprite graphics, I think what I want to try is I want to try doing like a maybe a pendulum, like here. It's gonna look like here. I'm gonna put BRB screen on, and I'm gonna look up like a pendulum algorithm. Pendulum algorithm. It'd be cool to like draw one, you know? Okay, so it's modeled using differential equations. And I don't know how to do differential equations on the Commodore 64. So this might be a problem. That's really funny. Okay. Okay, maybe we will pivot. I don't know, maybe we try and make a game. Here, we can put our graphic back on. Maybe we try and make a game out of this. So we've drawn a bunch of little blocks onto the screen. And we have a ball that can bounce around in, predictable directions. Is there a game I can make out of this in 30 minutes? I don't think so. Whatever, let's just read about sprites. I'll leave this little graphic on. Introduction to sprites. In the previous chapters dealing with graphics, we saw that graphic symbols could be used in print statements to create animation and add chart-like appearances to our displays. A way was also shown to poke character codes in specific screen memory locations. This would then place the appropriate characters directly on the screen in the right spot. Creating animation in both these cases requires a lot of work because objects must be created from existing graphic symbols. Moving the object requires a number of program statements to keep track of the object and to move it to a new spot. And because of the limitation of using graphic symbols, the shape and resolution of the object might not be as good as required. Using sprites and animated sequences eliminates a lot of these problems. Okay, yeah, so sprites, you can just draw images. Their color can be changed. You have a lot of power. You can tell when they collide. Can be made to go in front and behind one another. Just follow the examples in no time. And by the way, okay, so this book. Look at this book. Okay, chapter 6, sprite graphics. What is this book? Okay, it says at the top of the screen, you probably can't read this. It says Commodore 64 user manual. Here's something. Computers used to come with manuals that would teach you how to code, right? Like imagine opening up your new MacBook and it comes with like a JavaScript manual or like a Python or a C manual. Imagine how insane that would be. Like, I don't think people would use it, right? But I don't know, computing used to be so much more interesting, I think. In some ways, in a lot of ways, computing used to be so much more interesting, right? People were encouraged to program their machines. And in fact, you had to. So here, if I stop this and I go home, right? When you open up a modern, when you're opening up a modern system, let's fake a ready prompt. When you do a modern system, it opens up and you have like a whole graphical user interface, but computers used to not be powerful enough to do that yet. So all you had was this. It's called the basic language monitor, the basic monitor. You can just write basic codes and you can do basic commands. So your computer forced you to know how to use it, right? You could read the manual and you could read and start understanding memory locations. You could start understanding how to code. You could start understanding how to do so much more than, what we do with computers today, which is just, open up the browser, type in youtube.com and watch YouTube videos, right? That's fine. That's cool. And to be clear, there are a lot of very impressive technical challenges that go on to do that, but it's completely opaque to the user, right? People aren't actually understanding what's going on when they use computers anymore. Whereas I guess back in the 80s, you sort of had to. So I think that's pretty cool. I think that's pretty interesting. The timestamp 5359. All right, we might get some clips out of this stream. And let me increment our chapter graphic here. I'll just put it on screen so you can see. Chapter 6. Okay. So Commodore 64 manual speedrun. It's really slow, not making good time, are we? Introduction to sprites. Okay, so we already read this. Sprite creation. Sprites are controlled by a separate picture maker on the Commodore 64. This picture maker handles the video display. It does all the hard work of creating and keeping track of characters and graphics, creating colors, and moving around. Okay, so it calls it the separate picture maker. This is the graphics card. Okay, it's telling us about the graphics card right now. So your mental model, right? CPU does calculations, graphics card does graphics. Simple as. This display circuit has 46 different on-off locations, which act like internal memory locations. Each of these locations breaks down into a series of 8 blocks, and each block can either be on or off. We'll get into more detail about this later. By poking the appropriate decimal value in the proper memory location, you can control the formation and movement of your sprite creations. In addition to accessing many of the picture-making locations, we will also be using some of the Commodore 64's main memory to store information, data that defines sprites. Finally, 8 memory locations directly after the screen memory will be used to tell the program exactly which memory area each sprite will get its data from. As we go through some examples, the process will be very straightforward and you'll get the hang of it. So let's get on with creating some sprite graphics. A sprite object, and you know what, let me just check. I haven't had my stream dashboard open. I maybe should. Yeah, top chat, zero chatters, 0 viewers. Expected. But you know, just in case. Anyways, let's keep going. So let's go on with creating some sprite graphics. A sprite object is 24 dots wide by 24 dots long. Up to 8 sprites can be controlled at a time, and that is abysmal. Wow. Okay, honestly, okay. So here's something. The Commodore 64 was the most sold computer of all time, the most sold home computer of all time. And I think it's by quite a lot still. In fact, let's just look it up on Wikipedia real quick. We can say most sold home computers of all time. Okay, let's see if we can find a list. Yep, it says Commodore 64 still. Wikipedia listed in Guinness World Record as the most sold Okay, yeah. It has been listed in the Guinness World Records as the best-selling desktop computer model of all time, with independent estimates placing the number sold between 12.5 and 17 million units. Yeah, so yeah, you can see it was a very highly sold computer, okay? And on the inside, it used the same chip, the same CPU as the NES. So here we can see CPU, most technology 6510, sorry. And I believe this is the same CPU that was in the NES. I don't know if it was the exact same one, but it was similar enough that we can call it the same, right? They were compatible instruction sets, etc., etc. I say this is abysmal because the graphics card in the NES, it can control, it's able to control 64 sprites at a time, not just 8. So, you know, that's fine. It makes sense that I guess a home computer might be different than a specific built for purpose game console. But you know, whatever. Oh, also, okay, yeah, another trade-off. All right, the NES has way less RAM than the Commodore 64 does. So, you know, there were trade-offs that were made. I'm not saying the Commodore 64 is weaker than the NES, but for graphics, yeah, definitely the NES. Okay. So, say you want to create a balloon and have it float around the sky. The balloon could be designed as in the 24 by 21 grid on page 70. The next step is to convert the graphic design into data the computer can use. Get a piece of notebook or graph paper to set up a sample grid that is 21 spaces down and 24 spaces across. Okay, so let's use our whiteboard here. Okay, maybe we can make. Can we make like a table shapes frame tool? No, that's not what we want. How do I do a table? Let's do dark mode. Okay. I don't have a Google account signed in. Here, simple online spreadsheet. Let's just use a spreadsheet. EtherCalc. No sign up, start writing instantly. Okay, so here, perfect. So if it has the same UI I'm used to, we should be able to select. Nope. Okay. The scroll bar. I want to resize a bunch of rows to be, you know, appropriately sized. 24, 24. How many across? 24 objects across. Okay, and I maybe could have done this beforehand. But I didn't anticipate that we'd be doing, pixel art. Or, wait. Online pixel art. Pixelart.com, free, start drawing. Okay, how do I change the canvas size? Perfect. Width 21 or 24. Height 21. New drawing. Is that right? Okay. Go ahead. This feels wrong. Wait. 24 wide by 21 dots long. Wait, what the heck? What do you mean by long? Dude, what? Height and width, brother. What is this width and length? Whatever, I'll figure it out in a second. 24 by 21 grid on page 70. What page are we on? Yeah, no, it's just wider than it is tall. Okay. So we make a grid like this. Now I have a grid. We can do pixel art. Perfect. Undo. Where's the undo button? There we go. Okay. Set up a sample grid. Across the top, write 128, 64, 32, 16, 8, 4, 2, 1. Okay, so that's not going to work. 128, 64, 32, 16, 8, 4, 2, 1. So we can just, into it. Maybe we can add, can I add a grid? Tool, colors, reference, preview, layer options. Okay, whatever. We can add like a grid, a pixel grid. Select, you know what? I can't, but that's okay. Tile mode, frame sequence. All right. You know what? We can worry about this later. So what it's about to tell us though is, yeah, so here's this 128, 64, 32, 16, 8, 4, 2, 1. Again and again and again. So what this is this is a binary number. So how do binary numbers work? So we can compare a regular number. So like, let's say we just have like the number 25. Okay, what is 25? What is 25? That's a good question. So you might remember we have two groups of 10, right? We have 10 plus 10 here. Bam. Or really here, we should write it as 2 times 10. 2 times 10. And then over here, we have two groups of 1. Or 5 groups of 1. Goodness, I can't speak. 5 groups of 1. And here, let's say we make it a bigger number. Let's say it's 325, right? So what is that? Oh, and what the heck happened to this? Bam. Let's fix our arrow. Okay, so what exactly is a number? Okay, let's explain how numbers work. And okay, so how do numbers work? So all right, we have how do binary numbers work? So let's say we have a binary number 0, 1, 1, 0, 0, 0, 0, 1. Okay, what is this number? How does it work? Well, we can start off by explaining decimal numbers, and that'll make way more sense. So let's say we have the number 325. What is this? So you might remember you were taught that this was 3 groups of 100, 2 groups of 20, or 2 groups of 10, and 5 groups of 1. So remember, you were taught this was 3 groups of 100. So let's say 3 times, So we can write 3 times 100. There we go. We have over here 2 times 10. And over here, we have 5 groups of 1. Okay, but do you notice anything odd about this progression? 100, 10, and then 1. Right, well, it's multiplied by 10 every time. Okay, so what this is, we have a system called base 10. Okay, this is how it works. So in base 10, and really in base 10, we start off with, it's not actually 5 times 1, it's 5 times 10 to the 0. Okay, which if you'll remember, any number raised to the 0th power is going to be 1. We can do the same thing over here and increase, right? Okay. And to the power of 2. So actually here, no. So one thing you'll notice about here, one thing you'll notice about 325 here is that it's 3 groups of 100, 2 groups of 10, 5 groups of 1. Okay? So 10, 100, 10, 1, it's dividing by 10 each time. And we can express this in a different way. We can say that actually this is 3 times 10 times 10. Okay? And remember, 10 times 10, that's 10 squared. So let's write it as 10 squared. 10 to the power of 2, right? Let's copy that over. 2 times 10. So we're going to decrement this by 1, right? Because it's 10 times nothing, so it's just 10. So 10 to the power of 1. We 2 here. And then over here, well, we just continue our pattern, the power of 0. And remember, any number raised to the power of 0 is going to be equal to 1. So in base 10, the number 325, right? 3 times 10 to the power of 2, 2 times 10 to the power of 1, and 5 times 10 to the power of 0. And that's how we get 325 in base 10. Well, let's think about our binary number from earlier. So very simply, it's going to be the exact same thing, except, and if and I'm sure you've noticed this, we can take this 10, right, from base 10, bring it down here, and we can see what we have is a new system called base 2. So all we have to do is replace this, right, with 1 times 2 to the power of 2. 1 times 2 to the power of 1, and 1 times 2 to the power of 0. And actually we can go back and we can delete the 1 times, because 1 times anything is the same thing. It's the multiplicative identity or whatever. 2 to the 0, 2 to the 1, 2 to the 2, and so on and so forth. So this is going to be 1 plus 2 to the power of 0, 1, 2, 3, 4, 5, 6. And also 5. Okay, so let's go back to our C64 manual here, right? And actually, let's get it big style. You'll be able to see behind the scenes. 128, 64, 32, 16, 8, 4, 2, 1. So what this is telling us is that this sprite is represented by the computer as its 3 8-bit numbers. So if you've heard of 8 bits, like 8-bit graphics or whatever, this is what it's talking about. Well, not exactly, but this is what it means. This is what it means. So we have ways of representing our sprites like that, like that, like that. So we have these rows calculated like so. So for row 2, it would be data 125, 192. So we can make this balloon like so. But the stream is close to ending. So why don't I just type this computer in, this program in, and then we can just see what it looks like. And I don't think I'm going to clip that last part. So sorry, but I explained binary numbers, so that's whatever. 1 rem up, up, and away. 5 print quote oh, and let me show you the screen again. 10 v equals 5 3 2 4 oops 2 4 8 rem start of display chip. Okay, so we have the start of the display chip in a variable, and I'm guessing we're going to use this variable to go through and to edit and write the graphics onto the screen. Uh, 11 poke v plus 21 with the value 4 rem enable sprite 2 12 poke 20 40 42 the value 13, and this is going to read sprite 2 data from the 13th block. Line 20 for n, goodness, oh gosh, 20 for n equals 0 to 62, read q, poke 832 plus n with the value of q, and then go next. So we're just going to read in the data from q, and we'll get more information on that in 2 chapters, so we're going to let it be. 30 for x equals 0 to 200. 40 poke v plus 4 with x, and that's going to update the x coordinates, and then poke 50 poke v plus 5 with x, goodness, which updates the y coordinates. And then line 60, oops, oh gosh, not line 560, line 60, we'll go to the next x, we'll increment our x, and then we'll loop, we'll go to 30. Oh, oops. 70, go to 30. Let's list our program. Okay, it all looks good. Now we need to write in our data, 200 data, and this is going to be just a long sequence of numbers, 127, 0, 1, 255, 192, 3, 255, 224, 3, 231, 224. Okay, 210. Data 7, 217, 240, 7, 223, 240, 7, 217, 240, 3, 231, 224, 220, data 3, 225, or 255, 224, 3, 255, 244. It's probably gonna look awful, guys. I probably made a mistake already. 255, 160, 127, and 64, and 230. What the heck? Okay, so what we're doing here is we're typing in, we're manually typing in the some graphics here. That's fascinating. So, you know, in a modern computer, what we might do is we'd use some kind of program, like you could even use MS Paint to draw graphics, and then we could use those graphics in our game. But on the Commodore 64, with no other tools installed, all we have is this, and we got to enter it in all manually. Out of data, error in 20. Okay, let's list. Line 20. 832 plus n with q, and then go next. 20 for n equals 0 to 62. Okay, so 200, 0, 127, 0, 1, 255, 192, 3, 255, 224, 3, 231, 224. Bam, 200 works. 210 data. 7, 217, 240, 7, 223, 240, 7, 217, 240, 3, 231, 224. Okay, line 210 is correct. Okay, line. Oh, line 240. I completely missed that one. 0, 62, 0, 0, 62, 0, 0. All right, maybe just didn't write 62, 0, 0, 28, 0. Okay, now run. Out of data. Okay, it looks like something is getting corrupted. So let's go over here. Data, enter. Let's write line 230. Shift, insert a space. 1, 2, 3, 4. Data, space. I want it to read 0. List. Oh, 2400, clear, list. 200, 210, 220, 230, 240. Run. Okay, and here we have our little sprite graphic. Oh my gosh. Isn't that the coolest thing ever? Oh my gosh. Wow. We got a sprite moving. It's moving in the wrong direction. Okay, let's... And it's still on the screen. Oh, it's funny. Okay. Did I make any mistakes? 0 to 62, 0 to 200, v plus 4x, v plus 5x, next x, go 230. Flying across the sky. Okay, x coordinate v53, 248. Poke 2042 with 13. 0 to 62, read q. Poke 832 plus n with q. Go next. Okay. Wow, okay, that's so cool. Oh my gosh. Let's what is it? Like this. Wow. Okay, that's awesome. That is amazing. Man, I think that's the perfect place to stop. We have our beautiful little sprite moving across the screen. Isn't that the coolest thing? Wow. Okay. Yeah, wow, that's pretty cool. Actual screen photo. Ah, beautiful. Look at this beautiful Commodore 64 screen photo. I made it big for you. There are only a few things necessary. Goodness. Oh, there are only a few things necessary to actually create a moving object. And you know what? No, we can save the rest for later. Wow, look at us go. We have a sprite moving across the screen. We've got real graphics. Ain't that the coolest? All right, I think that's the perfect time. I'm gonna drop off. I gotta go back to work. It's been real. Sorry about the technical difficulties. Sorry that this stream appeared so short, or the VOD's gonna be shorter. You can see it's an hour and 20. I was streaming for 40 minutes, and I guess the stream just like never connected. I need to be more diligent and not assume that it's working and just really manually confirm it's working. But anyways, yeah, that's enough from me. Subscribe to Code Orangutan if you're not already. Thanks for watching. Be back with more Commodore 64 programming in 2 days on Wednesday at noon. So